Okay, so continuing again from this from the last video, remember that when we go this tau yz tau zy is equal minus mu this and this one can be, you can look at this in the Bird, Stewart and Lightfoot book, or if not, then you can also look at my slides, the video that I put before this one. This one will be equal to 0 because Vz is not a function of y. Again, look into the postulations before that we put in here. The Vz is only a function of x. So when it is not a function of y, that the derivative of a constant will become 0. And likewise, this one also becomes 0 because Vy is equal 0. Okay. So meaning that this one will be equal to 0. And then this particular term in here, rho, Vy, Vz, this will be equal to 0 as well because this Vy is equal to 0. So you go back again and look at the postulations in here. This postulation is very important and it will tell you everything. Okay. After from these derivations, then you can see that this tau yz is equal to 0. These things in here has a different symbol in here, phi yz. So this can physically be think like as in the flux of z momentum in y direction. Okay, so this one we are dealing with the rate of that momentum in a cross surface at y equal 0. Beside the in component, we need to also check about the out component as well. Rate of z momentum out across surface at y equal w. So again, we look into the system, into our system again on top. Okay, so this was the in. Then we need to inspect the out. So the same surface area is used again. Okay, so this one will be L delta x yz w L delta x tau yz plus rho Vy Vz at y equal w. With the same derivations that we do for the in components, this will become 0. Okay, so then the next one that we need to discuss is the other rate, the other momentum component, rate of z momentum in across surface at z equal 0. So again, we look back into the shell elements again. The key in here is the shell elements. So where you look at this at z equal 0. So at z equals 0, meaning which part of these things in here? At z equals 0, so this will be the particular surface area. So we are dealing with this particular momentum, combined momentum flux, and then we have another combined momentum flux over in this side as well, and then we are dealing with the area of interest in here. Okay, so the area of the interest in here is delta x multiplied by w, because because this particular width in here is equal to W, and then this particular thickness of the film in here is equal to delta X, because we are dealing with the shell element. Okay, so that's what we're gonna do. We continue with W delta X multiplied by the combined momentum flux of ZZ, Z equal 0. Okay, note that because we have this ZZ, so the first direction is the same with the momentum transfer directions. That means we have a components of pressure in here. Okay, so there will be P plus tau ZZ plus rho VZ at Z equal 0. Okay, and then that's the same with the rate of Z momentum out across surface at Z equal L. The same surface area is used again in here, W delta X multiplied by this ZZ at Z equal L, W delta X pressure tau ZZ plus rho VZ at Z equal L. Okay, so we have done with this Z momentum on the Z directions. The next one, we still have another momentum component. So this one is the rate of Z momentum in across surface at X. So we go back into the shell elements again in here. You look at your X in here. Your X in here will be here, these directions in here, and then we have this outer direction. That one will be the in. This one is the in. This one is the out. So the surface area of interest will be this particular area in here. Okay, this particular area in here, and then this particular area in the bottom as well. So the particular area is L multiplied by W, because the length of this shell elements will be L, and then you have the width of this one will be W. Okay, so that will be L multiplied by W. L multiplied by W. This one XZ X LW XZ plus rho Vx Vz at X. You can see that this X, this Z, and then this will translate to X and then Z, and then this XZ is also translated to the same XZ as well in here. Note that for this component, this will be 0 because Vx is equal 0. Again, you look at your postulations in here. You note that the Vx is equal 0 in there, and then Vy is equal to 0. So now we almost done with inspecting 1, 2, 3, 4, 5, 6 momentum component. Okay, so that is basically the thing that is of interest is the momentum. All the momentum component is need to be considered to get the derivations. Okay, and then this one will be tau Zx is equal tau Xz will be equal to minus mu del Vx per del Z plus del Vz per del X. Then again we connect this one again with the postulations. This will be equal to 0. Why? Because your Vx is equal to 0. This one on the other hand is not 0 because your Vz is a function of x. So the derivations of Vz with respect to x is not 0. That one will be the in. So now we're dealing with the out. Rate of z momentum out across surface at x plus delta x. Then same with here again. We derive again the same thing. L w phi xz x plus delta x is equal LW tau xz plus rho Vx Vz x plus delta x. Okay. That we basically finish considering all the momentum, but it's not finished yet. So we have an additional term in our momentum shell balance. This term is called the gravity. So we need also to consider the gravity force that is acting on our shell elements, because our shell element in here is representing a fluid with the shape of the cube. Okay, so this will be equal to the volume of your cube, LW delta x multiplied by rho g cos beta. So how this rho g cos beta come into? Why does it have a shape like this? Because it basically, if you consider this is the directions of the force. Okay, you draw a triangle, for example, where this triangle basically have a 90 degrees Celsius, 90 degree. Okay, then this one is what we call is the force of the gravity in the z directions, and then this one is the real gravity, rho g. And if we take an angle in here is beta. Okay, so this, note that this one is per unit volume. So you go into your trigonometry, then you will know that the cos beta, if you see these things, then you see that this Fg divided by rho g. Because then after that you can get this Fg, the force of the gravity on the z directions. So this one is on the z direction, will be equal to rho g cos beta. So this is where this term came from, rho g cos beta. Okay, then next we can, after figuring out all this term in there, then we can make the momentum balance. Your momentum balance is basically in by convective minus out by convective, and then plus in by molecular minus out by molecular, and then plus force of gravity acting on your system. Okay, now in here we we can if we go back here again, we are being clear that this term will be equal to 0. This will be equal to 0 because of this one is equal to 0, this one is equal to 0, so we don't need to consider this term further. Likewise, also the momentum out across this surface for this one will be 0. But then we need to check this term, and also on this term as well, and then also on this term as well. So we need to substitute all these terms into our momentum balance. So let's start with putting that thing in. W multiplied by delta x phi zz, z equals 0 minus W delta x zz at z equal L plus L W xz at x minus L W xz at x plus delta x plus L W delta x rho g cos beta is equal 0. Okay, I will cut this video in here, and I will start again to continue from this part. Thank you for listening.